So, a very good evening to everyone. On behalf of India Space Lab, I warmly welcome all the participants to today's session of Summer Internship and Training Program. It is a matter of great privilege to introduce our esteemed guest for today, Dr. Harishankar Sir, who is a scientist engineer at Indian Institute of Remote Sensing, IISR, ISRO, under the Disaster Management and Studies Department. Dr. Harishankar specializes in areas such as digital and communication electronics, SAR interferometry, land deformation analysis, GIS-based transportation systems, and geostatics. His research work focuses on advanced remote sensing techniques, including POLSAR and INSAR processing, land deformation monitoring, soil moisture estimation, and transportation network optimization. He has also contributed significantly through various research publications, conferences, and academic activities in the field of remote sensing and geospatial applications for disaster management. So, we are truly honored to have you with us today, and we look forward to learning from your valuable and knowledgeable experience. With this, I respectfully invite Dr. Harishankar Sir to take the session forward.
Yeah, thank you so much for the nice introduction. So, is my screen visible to all? Hello, anybody can respond?
Yes, sir, your screen is visible.
Okay, fine.
And
So,
also, I'm turning on the chat for everyone, and I request all the participants not to spam messages in the chat.
okay, fine. So, today's topic is GIS-based road transportation network analysis. So, I hope most of you are already aware about the GIS. So, stands for the Geographic Information System, which is a simple computer-based system where we can solve the problems having the Earth-related information or Earth-related data sets, whether it is spatial data or the non-spatial data sets. Okay, so this computer-based system we can use to analyze the problems related to the road transportation networks. Though there are different types of the transportation networks like the railway network or waterways or airways networks, but this lecture is focused on the road transportation network analysis, and the major focus will be on the city level network, useful for common public or useful for business purpose and so on. Okay, so I will start from the very basic, because to explain this lecture I will take the help of graph theory, a very famous branch of mathematics, and the operations research, which is another branch of mathematics, where we understand the optimization things. So, operations research will be helpful, and the graph theory, and then GIS. Okay, these three things are very important to understand this lecture. And we will also discuss what types of the problems we have related to a road transportation network and how we are using them on daily basis. So now coming to the definition of the a network. So network, as I mentioned, it is a kind of the graph. So graph is nothing but a function of the vertices and the edges or the line features. So in general, we can say the G is a graph. So graph equal to a function of the vertices and the edges. Edges are also called the arcs or the lengths or the lines. Vertices are the like the junctions or the nodes or the point features. So point features are the zero dimensional features, and edges are the line features, which is one dimensional features. So you can say a graph is a system of zero and the one dimensional features, Zero dimensional means point, and the one dimensional means the line features. There is no polygon features involved in the graphs. So it is a system of the point and line features. In simple way, we can say like this. Okay, but here it is important to understand the V is a vertex or the node, but it is not a single vertex. It is again a set of vertices. Okay, here you can see the V vertices of a graph are so many, like v1, v2, v3 up to vn. So n number of vertices may be there. Same way, the edges or the arcs are also not a single arc. These are the set of arcs. So each equal to e1, e2, e3 up to, let us say, em. And the arc can also be represented like the line is connected between the 2 points. So we can say from line is a feature connected between the 2 point features or two vertices. So this is another representation of edges, like b1 to bi to bj. So arc, a particular arc can be drawn from bi to bj. Okay, so this is the simple definition of the graph. But here the graph we are considering as a network, because now this is a network of the point and line features. And in reality there are number of examples of the network where we have only the point and line network line features. So road transportation network is the best example of point and line features. So you can say whether it is these are the streets or the main roads, minor roads, or highways, or the state highways, national highways, or the expressways, all are the line features. And wherever we have the roundabout or the junctions, so those are the point features. So we can say these roundabouts or the junctions can be represented by the point features, and the roads can be represented by the line features. Okay, so this is the best example, but the same thing can be applied over the other types of the network, whether it is railway network or the waterways or the airways. So, but keep in mind, these point and line features should be physically available, or you can say these point and line features should be physical features. They should not be like the imaginary line features or imaginary vertices. For example, if you see the meridians or the parallels to represent the coordinate system of the earth system, so those meridians are basically the line features, but those line features are just like the imaginary kind of the line features. So a network represented by the meridians or the parallels cannot be considered here as a graph or the network. Okay, so just make sure these vertices and the lines are some physical lines or physical point features. So here you can see, suppose this particular network I am drawing, so different types of the line features are connected with each other. So when we say the term network, it means the connectivity among the features is very important. If suppose 100 features are there but they are not connected with each other, then we cannot say that is the network. So all those features should be connected with each other, not like this every feature should be connected with every other feature. This is not like that, but they should have some connectivity between them, so that the from one features you can reach to the another feature. So that way it is called the connected network. So this is the example, like this line feature is connected with this line feature, as well as this line feature, as well as this line features. So this is the example of the connected network. If suppose features are not connected, then they are called the disconnected network. For example, this one, this whole we, if you are considering as a network, then see this portion of the network is connected, which consists of the point as well as the line feature. So this portion is connected, but this point feature and this line feature is not connected with the original body of the network or the graph. So this types of the network as a whole is called the disconnected network. And if we see, this is the third example where the connectivity is there between the point and the line features, line and line features. Yeah, so the connectivity may be of two types, means connectivity between the point and line, line and line. There is no connectivity between point and point because points are physically separated, so they are not in directly contact with each other, but they are in contact through the line features. So you can say the connectivity can be established between point and line features and the line and line features, not like the point and point features. So you can see all these features. Now I will call them as a feature, whether it is point feature or the line feature. They are connected to each other, but when you are able to see the lines, some arrow is also mentioned. So this arrow is also important, and this represents the flow of resources, or you can say the direction of flow of resources. So this arrow over this particular line is this towards this side, which means the resources can flow from this side to this side only. The resources cannot flow from this side, from this side to this side. So reverse flow is not possible, but in the forward direction the resources can flow. So if this direction or this arrow is mentioned in each and every line, then the network is also called the directed network. Means the direction of flow of resources is mentioned in the network, and hence the network is directed network. Okay. If suppose in this example the lines are not having those types of the arrows, it means this is undirected network, and this is directed network. Okay. And most important thing is the location of these point features. Location means all the point or the line features are lying in the same plane, or they are lying in the different plane. If they are lying in the same plane, then the network is called the planar network. If they are lying in the different planes, let us say in this three features are in one plane and remaining features are in the another plane, then that this type of the network is called the non-planar network. Example, if in a plane area a road network is there, so all the roads line features and the point features are lying in a single plane, and the network is called the planar network. What if you see in the metropolitan cities, most of the roads are on the earth surface, but in between some flyovers are also there. So flyovers are considered in a different plane, and the other roads are considered in the another plane. So in that case, those networks are called the non-planar network. So there are number of things are coming, or you can say this is the classification of the network. So here you can see all these features are connected with each other, so it is connected network. Suppose all the features are lying in a single plane, then it is called planar network. Here again, these features are not connected with these features, so this is called the disconnected network. And if all features are lying in a single plane, then it is called the planar network. If they are lying in different plane, then it is called the non-planar network. And this one, suppose all features are lying in a single plane, then it is planar network. If they are in different plane, then non-planar network. All features are connected with each other, so this is connected network. Direction of flow of resources is also mentioned, so this is directed network. Okay. But keep in mind the directions may be two way also. For example, over this particular road, this side row arrow is already mentioned. If this side arrow is also mentioned, it means the flow of resources is possible in both the directions. Okay. For example, if only one arrow is there, it means this is the one way road. If both sides the arrows are there, it means that is the two way roads. Okay. It means if, the resources can flow in either directions. Here in case of road transportation network, the resources are the traffic or the individuals who is basically moving around the road network. Okay. So but another example, for example, the pipeline network. If you see the water pipeline network or gas pipeline networks, those are mostly unidirectional networks. So unidirectional means if only one direction is mentioned. If two sides of the arrows are there, it means movement is allowed in both the direction, and that type of the network is called the bidirectional network. Okay. So you can say this is undirected network, this is directed but unidirected network. If arrows are in both the direction, then it is bidirectional network. Okay. And then if we are moving to the next example, so here you can see all points are there in the same plane. So it can, you can say this is the planar network, all are connected with each other, so this is the connected network. Then direction of flow of resources is also mentioned by arrows, so you can say this is the directed network, but it is unidirected network. And along with the line features, some number is mentioned. Okay. And that number is called the weight function, or you can say the cost function. So the weight function is representing the cost of flow of resources from this end to this end. Suppose if you are moving from this location to this location, then how much money you are spending. So that money is nothing but the cost function. Here, in terms of graph theory, we call it the weight function. Okay. So this weight function is very important, and this weight function is associated with each of the line. And if this weight function is associated with each line, then it is called the weighted network. If this weight is not assigned with the line feature, then it is called the unweighted network. Then this weight is very important in our case. Basically in case of the road transportation network, this is the simple transportation cost from this place to this place, and the transportation cost can be calculated by different ways. If you think how we can calculate this weight function. So suppose you are moving from here to here, so how much you are spending? Not only like if you are using the public transport and you are paying some money, and that is the only the cost. But if you suppose you are moving by your own vehicle, then how much fuel you are the fuel is consumed by the vehicle, and the cost of fuel is called the cost function or the transportation cost. Okay. So in general, if you see, I will come back to the calculation of this weight function, how to calculate this function. Means what is the meaning of 5 or 7 or 9 or 8, like that. Okay. And what is the unit of this weight function? Means unit is 5. What is the 5? 5 rupees or 5 kilometer or 5 minutes, what it is actually. Okay. So the unit we will discuss again, but keep in mind with each line feature some number is there that is called the weight function, but in GIS we call it the impedance factor. Okay. So this impedance factor is very very important. So if this impedance factor is mentioned with each and every line feature, then it is called the weighted network. So now based on these things, you can classify or rename the network like this: connected network versus disconnected network, or the graphs. Okay. So I hope you understand. Connected means if all features are connected with each other, then connected; not connected, then disconnected. Directed network means direction of flow of resources mentioned, then directed; not mentioned, undirected. If mentioned and mentioned only along the one direction, then it is unidirectional. If mentioned in both the direction, then it is bidirectional network. Planar versus non-planar graphs of the network, it means if all features are lying in the same single plane, then planar network. If lying more than one plane, then it is non-planar network. Especially in the hilly regions, the networks are non-planar networks. And weighted versus unweighted graphs means if weight is associated with each line feature, then it is called the weighted network. If not mentioned, then unweighted network. Okay. So these examples, you can say this is the connected, unweighted network, planar network, and the undirected network. Means in terms of these four categories, you can assign to the these graphs. So this is disconnected, unweighted, number is not there; planar, all are lying in the same plane; undirected, flow of the resources is not mentioned; connected, all are connected; unweighted, weights are not there; planar, all are lying in the same plane; directed, direction of flow of resources is mentioned; connected, all are connected features; weighted, weights are also mentioned; planar, all are lying in the same plane; directed, direction of flow of resources is mentioned. Okay. So the weight function or cost function, the weight function, again, you can think of this weight function. Suppose this weight function is 5. 5 is the representing the transportation cost, and transportation is taking place from which, in which direction? It is arrow is towards this side. It means the vehicle can go from this side to this side. It means the transportation cost is only possible from this side to this side. It means this is the unidirectional network. It means only one weight function is required for this particular line. It means this is the unidirectional weight. So weight may be bidirectional also. Suppose movement is allowed in both the direction, then you have to assign two numbers, means one corresponding to each direction. So movement is from here to here, so one number. Movement from here to here, another number. And both the numbers may be same or may not be same, depending upon the type of network. Suppose you are going from Dehradun to Delhi, the transportation cost may be same or maybe slightly different from Delhi to Dehradun. Okay, or for example, from Dehradun to Mussoorie, you are moving, upward direction, and then Mussoorie to Dehradun, again, transportation cost may be different. Okay, so this weight function is required for each line feature, sometimes only one and sometimes twice or two numbers. Okay, so in case of unidirectional network, only one weight function is required for each line. For bidirectional network, two functions are required. Okay, and this value generally we are putting as a positive number, but it may be negative number also. Or what we can do actually, we can assign these weight functions for both the directions. Let us say from here to here the number is 5, and from here to here the number is 6. This is generally representing the transportation cost along that particular direction. So this number, if it is positive, it means the movement is allowed. Positive number, positive weight functions represent the movement is allowed. If you are putting negative value with that weight function, it means the movement is restricted, or you can say movement is not allowed in that particular direction. Okay, so then question is how we can basically assign these numbers, means two numbers with the same line in GIS system. So if you have knowledge about the GIS system, like database preparation, so in database we can store the spatial and non-spatial information together. Non-spatial information you are putting into the in the tables, that is called the tabular data or the attribute data, and spatial data you can digitize in the database. So both are linked together. So what, how you can basically decide these weight functions? If you are assigning, listen, let's say the weight function from here to here, let us say you are giving the name like from to impedance, or you can say from to weight function. So from to weight function you are putting 5, and the weight function just opposite of this, means from here to here, it is called the to from. So to from weight function you have to give another value. And database table is just like the Excel file. So in one column you are putting, header of the first column is, let us say, from to. In another column you are putting to from. So from to is 5 and to from is 6. So that way in both the directions you can assign the weight functions. And suppose this is only unidirectional network. Suppose from to is allowed, to from is not allowed. So in to from you are putting 6, but put -6 so that the to from movement can be restricted. Okay, so whenever you want to decide, okay, in my city these number of roads I want to assign as a one way road. So for those roads or those line features, you can assign the negative impedance factor or negative weight function, or the weight function, negative wave function in the direction in which you want to restrict the movement. Okay, so that way you can handle. And now another very simple question comes, how we can say from here to here it is from to, and opposite of that is to from, opposite of to that is to from, that is fine. Means the moment you are deciding the from to direction, then immediately you can tell to from direction also. Means, but question is how you are deciding from to. From to is from here to here or from here to here. So it becomes very difficult to assign the from to. So means first one is difficult. The second one you can decide easily, because this is the opposite of the first one. So suppose why I'm trying to say here is, suppose this network you are not digitizing, because nowadays all the networks are already available on the internet or OpenStreetMaps. These network you can take from the OpenStreetMap. Okay, then you have to assign the impedance factor to each line features. So how you can assign? Because you have to basically go along with the each and every line feature, and then decide, okay, you are deciding, let us say from 2 is this side, from 2 is this, another person is deciding from 2 is this side, then it will be basically confusing. Okay, if this same database you are making open and people public is using, then the public may be confused. So whatever the standard you are following, that should be uniform. It should not be confusing. Okay, so or let us say partly you are creating, means in part of the network you are deciding, the negative or positive impedance factors. In another part of the network another person is deciding. So what is the criteria of deciding from to and the to from directions? So this is very simple actually. Simple in the sense, suppose you are digitizing this network. First case I am considering. Suppose you are generating this network, then how you are deciding, or if you are taking the OpenStreetMap, then how you are deciding. So first one I will consider first. Suppose you have digitized this network, then you are aware that I have digitized this this line feature from here to here. If you have digitized this road network from here to here, then from to is this side and to from is just opposite side. Means from to impedance factor is the impedance along the digitization direction of that particular line feature. So basically you have to identify that particular road is or was digitized in which direction. So along that direction, you have to decide that direction is from to, and just opposite of that is the to from. So suppose you have digitized the network, then you are aware, okay, I have digitized this roadwork from this side to this side, not from this side to this side. Means if you have digitized, then you are aware. But if you are taking the network from the OpenStreetMap, someone else has digitized this network, then how you can understand the road was digitized from which direction to which direction? Okay, so that is also possible. So one functionality is there in the GIS system, that is called the symbology. So you can assign the symbology to each line features, where the arrow based symbology is also there. So in the forward direction arrow, backward direction arrow, those kind of the symbols are there. So in forward direction arrow, you can assign. Then over each line feature, that arrow will be highlighted, and you can easily understand. Okay, this is the digitization direction of that particular road, and accordingly you can assign. Okay, this is the from to direction, and reverse of that is to from direction, and along both the directions you can give those weight functions. Okay, so that is the similarity, basically similarity with the GIS system. Because in GIS system, when you are preparing vector data sets, so data sets have three types of the geometries: point geometry, line geometry, and the polygon geometry, which means all the features on the surface you can represent in terms of either point or line or the polygon. There is no fourth geometry which is required to represent the all the features on the surface. Only these three are sufficient. But in network analysis, the third one is not useful. Only first two are useful: point and line features. It means if you are digitizing a network in the GIS system, it is easier than the database preparation, actual database preparation in the GIS. Okay, because polygon features are not required here. So once so digitization of point line feature is very easily, and then once this network is ready, then you can perform different types of the analysis. What kind of analysis, that we'll discuss later. But here, another important thing, I'm coming back to the weight function, because weight function is very, very important. If you understand the weight function, then in most of the cases, you can handle the solution of the problem very easily. So we have already discussed the from to impedance, to from impedance, that is fine. But now coming back to those numbers, what are these 5, 7, or 8? Suppose 5 is from to and 6 is to from. So then we understand, but what is 5? From where this 5 is coming? Okay. So 5 is, we understand both the numbers are associated with the transportation cost. Then thing is how to calculate the transportation cost that for that particular road. So the transportation cost, generally we calculate with the help of the travel distance, means the length of the road. If road length is large, means transportation cost is large. If road length is small, transportation cost is small, which means if longer road is there, the number is larger. If shorter road is there, it means number is smaller. So now we have some idea, like if we are calculating the transportation cost according to the travel distance. Generally, it is a general perception. More distance, more transportation cost. Less distance, less transportation cost. Okay. So according to the travel distance, we can calculate this value per unit cost. Let us say per unit distance we have the cost. Then simply multiplying the length of the road, and we will get the number. But this is not always true. More longer road means longer transportation cost, smaller road means smaller cost. This is not always true. Sometimes it may happen the road is longer but travel time is very less. Sometimes the road is smaller or shorter but the travel time is more, especially in the cities. Okay. If more travel time is there, then again you have to spend more money, means transportation cost should be large. Which means here I am trying to say that if you're calculating the weight function, so you cannot completely rely on the length of the road or the travel distance only. You have to consider another dimension also, which is travel time. Okay. So more travel time, then more cost. Less travel time, less cost. These are directly proportional relationship. More distance, more cost. Less distance, less cost. More travel time, more cost. Less travel time, less cost. But question is, can we combine both of them, or we should keep both of them separate? Suppose I am writing from to distance impedance. You understand? From to distance impedance, which means I am calculating the weight function according to the travel distance, and I am putting the numbers. So from to travel distance, from to, or to from travel distance, it means I have calculated the impedance factor according to the travel distance. Another way I can write, let us say, another columns of the database table, from to travel time, to from travel time, and that travel time I can mention along both the direction of the road. Okay. So what happens? I can have some flexibility when I'm solving the problem. That time I can choose. I want to use the distance as an impedance factor or time as an impedance factor. This is the flexibility. Suppose you see in Google Map, when you are searching the shortest path, so it is showing total distance, travel distance, total travel time also, and you can take decision whether you want to travel longer distance. Basically you are taking the decision based on both the values, but the value should not be like the travel distance is only 5 kilometer and travel time is 5 hours, so that type of the route you will not opt. So there is a flexibility in the Google Map. They are providing the total travel distance as well as the travel time. It means they are calculating the shortest path based on the distance impedance also and based on the time impedance also. Okay. Now, Another thing I can mention, suppose you are representing the impedance factor in terms of travel distance, then the unit you should mention this 5, let us say meters, because travel distance is in is a basically distance. So distance means the unit of distance you have to mention. So whether it is 5 meters or 5 kilometers or 5 miles. Okay, when you are representing in terms of travel time, then you have to write like 5 seconds or 5 minutes or 5 hours, something like that. Means if you are calculating the impedance factor from the travel distance, then in that case the unit of impedance factor is the unit of distance. When you are representing the impedance factor from the travel time, then the unit of impedance factor is the unit of time. Okay, so here you are able to see only the 5, but it may be 5 meters, it may be 5 kilometers, or it may be 5 minutes or 5 hours or 5 seconds, something like that. Okay, so those numbers are not mentioned here. Sorry, those units are not mentioned here. So those units you have to take care in the database, or in the header itself you can mention travel from to distance and underscore, let us say in meters, underscore in, let us say in kilometers. So that way you can mention the header name. So whatever the value you will put below that column, it means those values are in that particular unit. Okay, so now another interesting thing here is, so now you understand the unit of impedance factor or unit of cost function is not only the unit of money or rupees or dollars. This is the unit of impedance factor is in this case the unit of distance or unit of time. Okay, now another interesting thing here is, if we are measuring this impedance factor according to the travel distance, so distance is fixed. The distance between this vertex and this vertex is fixed. Whether it is 5 kilometers, it means from to distance is 5 kilometers, to from distance is also 5 kilometers. Both the distances are same. But it means in that case, if you are calculating the impedance factor from the travel distance, so from to impedance is equal to from impedance. You just keep in mind. But if you are calculating this impedance factor with the help of the travel time, then the from to travel time may or may not be same to from impedance factor or to from travel distance, travel time. So in that case, when you are calculating impedance factor from the travel time, that from to impedance may or may not be same to from impedance factor. So in that case, I have taken the 5 and 6. From to is 5, let us say minutes, and to from is 6 minutes. Okay. So this is one important thing. But see, if you're calculating from the impedance factor from the travel distance, then distance is fine, because whenever you are digitizing this network in the GIS system, so the length of each feature is given in the database itself, because software itself calculates the length of the roads. So distance is there is no need to calculate the distance. That distance is already there in the database. But time, travel time is not there in the database. That you have to decide. Means from to how much time is taken, and to from how much time we have to travel. Okay, so that calculation itself is very very difficult. Means if you are calculating the impedance factor from the travel time, so then you have to basically put that values. Then how to decide travel time? Means in a city network, how much time you have to spend from this location to this location, and from this location to this location. How to know? The same thing is applicable over the other roads also. But point is how to calculate that time. Do you have any idea? Suppose I have my own vehicle. I can go from point 1 to point 2. Then I can start my watch and I can note down the time. This is very traditional way. But that is not the standard way of calculating the travel time. So that may be very confusing. It may be I may be satisfied with this one, or other people may not be satisfied with this type of the calculation of the travel time. And more importantly, this is the driver specific. Suppose I have my own vehicle, but I am in free mood, so I am driving car with slowly. So obviously the time will be more. But other person is driving with another speed. Time will be different, and another person is driving very fast. The time will be different. So this one we have to put in this line as impedance factor, time impedance factor. So see, by uh, for simple understanding or theoretically it is fine, travel time is fine, but when you go to the practically, then you have to put that travel time for each and every road, and how much we have to put, that is very very basically confusing, and we are not able to get the actual travel time from one location to another location. And also more than that important, if you are going in the morning time or evening time or noon time or in between, these times may be different. So question is, which time value or which time impedance I have to put for a particular road. And nobody is and this is a very challenging task. We are not able to find out a very correct value of the travel time. And so point is, so that calculation where I was going by my own vehicle, so that kind of approach is not good. So we have to take another approach to calculate the travel time. So generally people what they are doing actually, they are using the formula distance equal speed equal to distance upon time. So distance is there, the road length is the distance, time you want to calculate, speed equal to distance upon time. Time you want to calculate, distance is given, and speed you have to decide. And speed means speed limits. Generally speed limits are mentioned on the road, that is the decided by the authorities, or the transport authorities or the pupil administrative authorities. They are mentioning, a speed limit over this particular road is this much. But keep in mind, so from if we are putting in this relationship, speed limit we are putting, distance is there, then we can calculate the time. Okay, so that time I can use as a from to time or to from time, because the speed limit may be same in both the direction or may not be same in the both the direction. So accordingly the travel time may or may not be same in both the direction. Correct. So that way people are using, but that approach is also not correct. If you see, in this relationship, distance is fine, that is fixed between these 2 points. Speed limit is decided by some authority, but the speed limit is the maximum speed by which we can travel or we can move. But generally, nobody is following that speed limit. Either moving slowly or moving fast, means beyond the more than the speed limit. But nobody is following exactly. Suppose speed limit is 60 kilometer per hour, so everybody is not moving with 60 kilometer per hour speed. So either less or more. So it means whatever we have calculated, that's not 100% correct. And keep in mind, we have taken the highest limit at the calculation of the time. It means if time something time after calculation some time is coming, it means the time, that much time is required if you are moving with the speed limit, or with the speed equivalent to the speed limit. Okay, if you are moving less than that, it means more time is required. So calculation of impedance factor according to the travel time is difficult, but we are using this particular approach, which is also not correct. But yes, for a starting of the problem solution, starting of the solution, we are assuming okay, travel time may be this one. Okay, so now both the things you understand, from to distance impedance factor, to from distance impedance, to from time impedance, and from to time impedance. Okay, either distance or time. But if this type of the calculation you are doing, then this types of the impedance factor is called the static impedance factor. Because static means these are the fixed in the sense distance between the 2 points is fixed, and the approach which you have applied for the calculation of the time, that is also coming fixed or the constant value, because you are using the fixed distance and fixed speed limit. It means time is also fixed. If time is fixed, means that is constant for particular road, that is not varying with respect to time. Time is not varying with respect to time. So it means that is the static value you are calculating. So this types of the calculations is called the static impedance factors. Please bear with me. I'm not changing the slides. Okay. So because a lot of things are associated with this particular slide. Yeah. So now coming to the static impedance factor or impedance function or the cost function. Both the calculation, whatever I have explained, those are static impedance factors. But when we go in any city, we cannot be satisfied with this, with the calculation based on this static impedance factor. No, you cannot be satisfied. And the routes may be, changing from time to time. Suppose you are going in a particular city from one location to another location. So the shortest route in the morning may be different, in the evening may be different, in the noon time may be different. It means the routes are changing depending upon the time of the day and the actual situations on the road, means how much traffic is there. If more traffic means more impedance factor, less traffic less impedance factor, and these traffic situations are varying with respect to time. It means that may be the actual way of calculating the impedance factor, not these the previous two ways which we have discussed. Okay. So point is, if you are able to handle the real life scenarios or real life situations or the real time traffic situations on the road, and then you are basically deciding the impedance factor, then you can satisfy most of the public. But this is again challenging task, how to basically change this impedance factor, according to the time. Time is variation in time. So suppose right now it is 5, after 2 hours it is 6, after 5 hours it is 5, after 10 hours it is 12, something like that. So this types of the impedance factor is called the dynamic impedance factor. So make sure static impedance factor and the dynamic impedance factors. But the calculation of dynamic impedance factor is very, very difficult. See, the static one was also difficult when we calculated from the time, travel time. That time we faced some problem in the calculation of time. But now, when we want to handle the real time scenario, situation, traffic situations on the road, then it becomes again very, very difficult because we don't know what is the situation of the traffic on road number 1 or road number 2 or road number 10. So if you really want to handle that type of the situation on the road, then you have to have the real time traffic information at your database, so that you can easily identify the impedance factors. Variability means at this time impedance is this one, at this time impedance is this one. So that impedance factor you can directly link with the traffic situation on that particular road. More traffic, more impedance factor, less traffic, less impedance factor. Okay, this is common sense. But question is, from where this real time traffic information will come to the database. So first and foremost thing is, we can install some sensors on the road, what is called the traffic sensors. So traffic sensors can capture the traffic information, and that information we can directly pull into our database. So in real time manner, we can have the traffic situation, and accordingly we can calculate the impedance factor, which is dynamic impedance factor. But question is how to calculate the dynamic impedance factors. As I
Excuse
mentioned,
me, sir.
yes.
Sorry to disturb, but once participants are having a lot of queries, can you please check the chat box once?
Okay, can we take this lectures, questions after the lecture or in between?
So I guess there are some general queries. So students are asking me to like
Okay, in the
tell you
chat
to check the
box,
chat
chat
once.
box. Okay, in the chat, what is the question? The
I request all the participants who have genuine question or query, please drop your question if it is very genuine in the chat box and sir will answer.
Yeah, somebody asking, the slide is not changing actually. Yes, I am explaining the first slide only. So wait for that. Okay. If this is clear, then the other things will be clear easily because this slide is very important. And what is the question? I think some students are not understanding the understanding type. Did not understand type. When no use what? No, I'm not getting their questions. There are not questions actually. They are putting anything like, okay. Anyway, so this real time traffic situation, yeah, I can go to the next slide, no problem. Okay, so the impedance factor may be dynamic in nature. Now coming to the network related problems, road network related problems, and then we can have some solutions also. So the first and foremost problem is the shortest path problem, which is shortest path is the path of the minimum impedance factor. Suppose you want to go from point A to point B, then there are multiple lines may be involved, linear roads may be involved. So what is the sum of impedance factors of all the lines should be minimum or the optimal. So that path is called the shortest path. And from the shortest path analysis, we can do the driving time analysis, means how much time is required to travel across the that particular route, and we can find out the optimal routing and the closest facility analysis. This is also important, especially during the emergency situations. So, like suppose some accident is happening at a particular location, or that is called the accident spot. So from that accident spot, suddenly we want to search the closest hospitals or the closest police stations. So closest hospitals, let us say within 5 minutes of travel time, or within 2 kilometers of the travel distance, how many closest hospitals are there or closest police stations are there. So that comes under the closest facility analysis. And then service area analysis. This is also based on the shortest path problem concept. Service area means like in a particular city, suppose five police stations are there. So the service area of each and every police station should be identified based on accessibility of the network, so that if any accident is happening within that particular area, so that particular police station can respond fast. Okay, so based on the accessibility of the road, the service area of each and every police station can be identified with the help of the GIS technology. And then driving direction can also be identified. For example, if you are going from one location to another location, so the driving directions will explain you, like you start from this particular point number one, then move towards the northeast direction, then from this point you take the left and move this much distance, this much time, then take right, and then travel this much distance time, and then again take left side, and so on. So the complete description of the entire route is explained in the text also. So that is called the driving directions. Okay, so if you understand the solution of the shortest path problem, you can handle the driving time analysis, optimal routing, closest facility analysis, service area analysis, and the driving directions. Okay, so this is very important problem, and everybody is using nowadays. Generally, people are using the Google map. And the second problem is the supply demand problem. This is mostly useful for the business purposes, like the traveling salesman problem or the vehicle routing problem. Traveling salesman problems job is basically they are taking some goods or the material from some depots or the warehouses, and they are selling to the individual households. So they are also searching the shortest path or the optimal path, so that they can minimize the transportation cost, and then they can sell the maximum goods or the services. Okay. And vehicle routing problem, as in this case the vehicle is involved. So this is again useful for the business purpose, where the people are loading the vehicles from the warehouse, putting the goods and materials, and then they are going to the individual retailers, and they are delivering the that much goods, and then from that retailers they are going to the another retailer, then another retailer. So that way they are delivering the goods and material to each and every retailer of their contact. And major objective is how to minimize the transportation cost, or how to minimize the impedance factor during the entire route from starting to the end. Starting is from the warehouse, and ending is also at the warehouse, and in between they are serving to multiple retailers. So during this particular journey, how to serve the customers and how to minimize the total transportation cost. Another problem, road network related problem, is the minimum spanning tree problem. This is also a very important problem. So this problem is the minimum spanning tree problem. This is widely used in the different government schemes. For example, the Prime Minister Gram Sadak Yojana is there. So the solution of that problem can be find out with the help of the minimum spanning tree problem. Then another problem is the Chinese postman problem. The postmen are also having their own problems, like they want to deliver the their letters to the individual households. So they are starting from the post office, going to the individual households, and then they are coming back again to the post office. So which route they have to find out? So that is not very easy to find out. So those routes can be find out very easily with the help of the GIS technology. And the maximum flow problems, this is applicable over the uh, water pipeline or the gas pipeline networks. So one by one I will explain. So now coming to the first shortest path problem. So shortest path problem, it's like if some network is there. For example, this particular network is here. These are the nodes, and line features are associated with each type of the line impedance factors. So suppose you want to move from this location to this location, from vertex S to vertex Z. So what is the shortest path from S to Z? So this you can find out with the help of the some algorithm, and the very rudimentary algorithm is the Discustra's algorithm. So how it is basically works, it this particular algorithm says you first identify your starting point, or basically the your origin and the destination. So let us say in this case the origin is S and the destination is Z. Then this algorithm says give the weight of the starting point as 0, and the weight of the other vertices as large as possible, let us say infinity. Okay. So the weight of this vertex is 0, and the weight of other vertices is infinity. Then this algorithm says now start from the origin, and explore all the possibilities to move ahead, and minimize the weight of other vertices as minimum as possible. So how it is basically done? See, the weight of this one is 0. Now from here we can move forward in by two ways, either through this particular direction or through this particular direction. So suppose we are moving through this one, then the weight of this vertex should be the weight of this vertex plus the weight of this line. So 0 plus 10 should be the weight of this vertex. So In that case, the existing weight of t is infinity, but the calculated weight, which is 10, is less than infinity. So we can update the weight of the this particular vertex. So infinity can be updated by 10, and this way the first possibility is over. Then we have to explore the another possibility from the starting point, which is this one. If we go this way, then we have one can reach to the vertex y, and the existing weight of y is infinity. And if we calculate the weight according to this particular path, so the weight of y should be 0 plus 5, which is 5. So the calculated weight is 5, existing weight is infinity. So in existing weight is more than the calculated weight. So we can update the existing weight infinity by 5. Okay. So the all the possibilities from starting points are over. So now one can reach either t or the y. So now from t again, we can move ahead, and whatever the possibilities are there, one by one we can consider. Let us say we are considering from this point. Okay, let us say this one. Yeah, this scenario I have explained. Okay, so now the weight of t is 10, and now weight of y is 5. Now from y or t we can move ahead. If we are considering t as a first, then how many ways are there to move ahead from t? From t to x or t to y, this way, because according to the arrow we have to move. So only two possibilities are there to move ahead from vertex number t. And how many possibilities are there from vertex number y? So one possibility is this one, another possibility is this one, and another possibility from y is this one. So three possibilities are there from vertex number y, and two possibilities are there from vertex number t to move ahead. So suppose we are considering one by one all of them. So suppose we are moving from t to x, then the weight of x should be 10 plus 1, 11. And 11 is less than infinity, so the infinity can be updated by, yeah, sorry, yeah, infinity can be updated by 11. And another possibility is from t is this one, we can reach to the y. So the weight of y should be 10 plus 2, and that way it is 12. It means the weight of y should be 12, but the existing weight of y is 5, and the calculated weight is 12. So the calculated weight is more than the existing weight, so we will not update the existing weight of y. So the weight of y will remain 5, not 12. Okay, so whenever we are getting a smaller value, then we will update. If not, we are getting the larger value, will not update it. Okay, now if we are moving from by, so by to z, the weight of z should be 7. 5 plus 2, 7. So 7 is less than infinity, so updated weight of z is 7. And if you go from y to x, so the weight of x should be 5 plus 9, 14, and the existing weight is 11. So weight of x will not be updated. And if you move through this particular way, then the weight of t should be 5 plus 3, 8, but the existing weight is 10. So the weight of t will be updated as a 8. Now again, new according to the new weight of t, again we have to move from t and move ahead and update the weight of the other vertices. So the situation is here like this. If you are moving from by first, then the weight of t is 8. And if we are going through this way, then weight of x is 14. And if you are going through this way, then the weight of z is 7. Then this way, the updated weights are 5, 7, 14, and 8. And if you are going through this way from z to x, then the updated weight of x is 7 plus 6, 13. Earlier it was 14, so it is updated by 13. And another possibility is this one, from t to x. If you are going to 8 plus 1 is 9, so 9 is less than 13, so the updated weight of x will be 9. And so this is the basically the minimum weights. Okay. So now the other vertices have the minimum weights. So here you can see, if you want to move from S to Z, the total transportation cost is 7. How it is, which is what is the route? The 7 came from 5 plus 2 and 5 came from 0 plus 5. So route from S to Z is this one, S to Y and Y to Z. So this is the shortest path from S to Z. And what is the shortest path from S to X? The total weight is 9. And what is the route? S to Y 5, then Y to T, then T to X. So this way one can reach from the origin to the destination. Okay. Now there are four possibilities. Here we have considered no fixed origin and the fixed destination. So your origin is fixed, destination is also fixed. Then this algorithm will proceed like this, whatever I have explained. But if other situations are there, for example, destination is not fixed, but origin is fixed, or origin is fixed, destination is not fixed, or both things are not fixed. So those situation I have explained here, like from a given means given origin means origin is fixed, to a given destination means destination is also fixed. So the solution of this particular situation is already explained. Then the second situation is from a given origin means origin is fixed to any destination, means from origin S is there but destination may be anything, so that can also be handled whatever I have explained. Okay. Because from S to Z I have explained, S to X is also there, and S to T if you want to move, so the total transportation cost is 8. That route will be S to Y and Y to T. So you can say from given origin which is S, you can reach to any destination. Problem is already solved. Or if destination is fixed, that is also solved. For example, initially you have to assume X is the destination and S is the origin, so the route is also calculated. So for first two situations the solution is already achieved. But what is the third situation? From any origin to a given destination means the destination is fixed but origin is not fixed. Means somebody wants to go from S to Z, or somebody from T to Z, or X to Z, or Y to Z. It means origin is changing but destination is fixed. So that situation is not covered in this particular solution. So what can happen in this, to handle this third situation? You have to run this algorithm by keeping the destination as origin and other vertices as a destination. Means right now we have run this algorithm from S to other vertices, but to handle the third situation you have to run the algorithm by considering destination as a origin and run the algorithm in the reverse direction. So that way from the destination to each vertex you will have the minimum weights, and you can solve the problem in the third situation. From any origin you can reach to the given destination. And the last situation is very important, that is called the from any origin to any destination. This is useful for the common public. Suppose I want to go from Dehradun to Delhi, somebody wants to go from Delhi to Bombay, somebody from Kolkata to Chennai, something like that. Means their origin and destinations are not fixed. Means the database is open to the public and anybody can go from anywhere to anywhere. So that situation is very important to handle the masses. So to handle the last situations you have to run this algorithm n times if n vertices are there, and in each run one vertex can be considered as a origin. So suppose in your network 1 lakh vertices are there, so you have to run this algorithm 1 lakh times, and then and in each run one vertex you can consider as a origin. Then the last situation can also be handled very easily. Then there is another concept called the successive path. For example, in this particular case, you want to move from S to X. Then the path is S to Y, Y to T, T to X. But suppose in by any region this particular route you are missing, suppose some construction work is going on between t to x, then this route is disturbed, or any disturbance is there between by and t, then this route is missed. Okay, so suppose anything is happening, so suppose we are taking this example from s to by to t, t to x. So this is the route. If something is happening between t and x, then this route you cannot find out, or you can say this first shortest path will be disturbed. It means you have to run the algorithm. You may get, this particular path from here, s to by to z to x. There may be another route. And suppose some disturbance is happening between by and t, it means this particular line is disturbed, then the whole route is disturbed, means from s to x. In that case, you have to run again the algorithm. That route may be from, let us say, s to t, t to by, t to x. Okay, or suppose this particular thing is disturbed, then the route may be something else. Let us say from s to t, t to by to x. So point is that in the first, whatever we have calculated, that is the first optimal path or first shortest path. If anything is happening in any of the line features for this shortest route, then you have to run the algorithm again, and you will get the another shortest path. Okay, so suppose we are putting some barriers over these lines. Suppose one barrier is put it over here, then you are getting the solving the problem, and you are getting the another shortest path. So the weight of that path is, let us say, w1, and in next run you are putting the barrier over this line, and then you are running again, then you are getting another route. Let us say the weight of that route is w2, then you are putting the barrier over here, and then running the algorithm, and you are getting another route, that is, let us say, w3. Okay, so now in this w1, w2, w3, you can arrange in the ascending order. So first one is w1, let us say, then w2, then w3, if they are arranged in the ascending order. In that case, the W1 is called the second shortest path, W2 is called the third shortest path, and the W3 is called the fourth shortest path. And the first shortest path is this one, whatever we have already done. So this way, the first shortest path, second shortest path, third shortest path, fourth shortest path, these paths are called the successive paths. Okay. So, whenever you are getting on the Google map, you are not only getting a single path between your origin and destination, you are getting some other paths also. Means second path, third path, and the fourth path. And those paths are basically the successive paths. Now, coming to the supply demand problem or the vehicle routing problem, the second very important problem. So, here you can understand, let us say this is the depot, or let us say warehouse, and these pink dots are the customer locations or the retailer locations. Okay, so what is happening, let us say in the morning, 9 o'clock, let us say 8 o'clock, the vehicle is there in the depot, and people are loading the vehicle, means they are putting some materials, name, type of the material, or the goods, or naming each and every items. And then what is happening at the 9 o'clock right time, the driver is ready to uh, take this vehicle to the individual customer locations, because they want to deliver this goods or material to the individual store locations. And suppose, and then the driver basically want to find out the optimal route from this depot to the individual customer locations, and finally come back to the depot. So let us say this vehicle has started from here, and 9 o'clock is started from here, and reached to this customer location. When he is reaching to the customer location, that time he is delivering the material according to the demand of this customer or this retailer. So the demand in terms of material or this goods, okay, after delivering it here, it is moving to the next customer location. Then when it moving to the next customer location, again delivering the material, and after delivering it is going to the next customer location, delivering some material, and then going to the next customer location, delivering something, and everything is finished in the vehicle. The vehicle will come back to the depot location. So first thing is very clear. So whatever the material is there in the vehicle, that amount of material is equal to the demand of all these retailers. Means somebody has demanded here, let us say T1, here T2, here T3 amount, here T4 amounts. So T1 plus T2 plus T3 plus T4 is equal to the capacity of the vehicle. Okay, so this way vehicle is started and coming back to the depot. So this is the solution. But how to find out the solution? Why this route is there from here to here, then here to here, then this, then coming back? The route may be like this also. First going to 2, then 1, then this, then this come back. So in that case, the travel distance of this vehicle will be large. If it is large, it means transportation cost is large. Okay, and the same thing can happen. Let us say 3 vehicles are there, then another vehicle is going or covering this portion or this side of the city, and delivering the material to the individual customers, and serving another part is this side. And let us say 3 vehicles are there, and routes of the 3 vehicles are something like this. Okay, so if they are planning the routes properly, so the transportation cost will be less. But if you handle the real time situation or the real life situation, then the real life situation is not this much simple, whatever I have explained right now. Means here we have satisfied, here we have kept only 2 things in mind. One is the capacity of the vehicle, should be the demand, material demand of the individual households, and the optimal route. But if suppose what happens, suppose the vehicle has started from depot at 9 o'clock and reaching to this customer location at 9:15 and delivering some material. And suppose that time this customer is not ready to take that material. Suppose that retailer is not free. Suppose some individual customers are more and he is busy to giving materials to the individual customers. So this retailer is saying, no, don't come at 9:15. I am not free at 9:15, come at 2:30 or 3:30, something like that. Means he is demanding another thing, means delivery time according to his choice. Then what will happen? The entire route of this vehicle will be disturbed. Means the transportation cost may be different. And same way, suppose the time demand for this customer is different. Suppose this customer is saying please come at 4:30, this customer, this retailer is saying please come at 11:30, this is saying please come at 1:30, or some other customers are saying okay, come, or let us say some customer is here, he is saying please come at 9:30. So they are basically giving their times, their choices. So of course the material demand is there, but now another demand is the time demand. So if you want to satisfy your customers, you have to serve the material according to their choices. Okay, so what will happen? This particular route will be disturbed. Whatever this route is identified, this is not disturbed. The route may be something like this. First, the vehicle is going to this customer, then coming to this customer, then going to this customer, then going to this customer, according to the time demand, then going to this customer, and then finally coming back to the depot. It means now travel distance is much larger than this particular route. But that is also called the optimization problem, because in this particular scenario the customers are not happy, or customer satisfaction is not there. But in the next case where the zigzag path was received, so in that case customers are happy. So for a businessman, if customers are happy, it means the businessman is happy. It means he has optimized, optimized the route. So in that case, the small demands can also be handled in the GIS systems, and this problem is related to the network only. And the small things can also be introduced. So for example, suppose this customer is saying please come at my place at 2:30, but vehicle may or may not reach exactly at 2:30. So sometimes it can reach up to 220 or sometimes 240, means little early or little late. So what is required? The vehicle should be parked at that customer location. So yeah, the vehicle has to take a permission whether this thing is allowed for me to wait at your place for 10 minutes or not, whether the sufficient parking is there or not. So according to the customer's choice, you can take the permissible time window for the waiting, or if some delay is there, then the delivery time may be extended or not. So such small demands of the customers or the retailers can also be taken into account, and the problem can be optimized. So the in order to satisfy all the customers, the route can be planned, and that route is also called the optimal route. But this problem is something like the supply and demand problem handled by the vehicle routing problem. Now another important problem is minimum spanning tree problem. So the definition of tree is very simple, like tree is also a graph, kind of graph, but that graph is a connected graph of n nodes and n minus 1 arcs. Suppose 5 nodes are there, then 4 arcs should be there, and there should not be any loop or any. For example, here loop means here, for example, this one, you are going from 6 to 4, 4 to 5, 5 to 6. It means this is a loop. You starting and you are coming back after. So here you are having the closed loop. This is also called the circuit. Okay, so this type of the situation should not happen. So you can say a graph of the n nodes, n minus 1 arcs without loops, connected graph is called the tree. So tree can have 2 vertices 1 arc, 3 vertices 2 arcs, 100 vertices 99 arcs, without loops, all connected. So this is the basic definition of the tree. But question is, for example, how we can apply this particular situation over different types of the problems. So I will take the examples of the Pradhan Mantri Gram Sadak Yojana. So what is the objective of that scheme? That scheme is basically, in our country there are so many villages which are not connected through the Pakka road. So the objective of the scheme is connect all the villages through Pakka road, and the total road length should be minimum. It should not be maximum. Means multiple roads are not allowed. So, means we should not basically create multiple roads to connect the villages. So how much minimum length is sufficient to connect all the villages? So this is the objective. So this objective can be achieved if you understand the solution of the minimum spanning tree. Okay. So here you can take the examples. Suppose this is the network. This is the planar network, and connected network, and the weighted network. Okay. Suppose these vertices are the locations of the villages, for example, and these lines, initial lines, are the lines, or you can say the roads, but these roads are the kacha roads. Okay, concrete roads are not there, or the metal roads are not there. These are the kacha roads. So you can say the distance from this village to this village is 16 kilometer, or this village to this village is 19 kilometer, or you can say the weight function is 19, or you can say if you are constructing this particular road from 1 to 2, then this much cost is required, and to construct this road this much cost is required, maybe in lakhs or millions, something like that. So this is the network. Now question is how to connect the villages through Pakka road, means how to pick these kacha roads to convert into Pakka roads, so that all the villages are connected through the Pakka roads. We cannot construct the Pakka roads over each and every Kacha road. Otherwise, the total road length will be maximum. So, if we connect like this, you see here, this to this to this, like this. So, total road length is, let us say, 6 plus 5, 11, plus 11, 22, plus 16, 38, plus 18, 56. So in 56 kilometer of the road length, all the villages are connected through the Pakka road. Means there is no need to put Pakka road over here or here or here or here. Okay. So if you are constructing like this, then all the villages are connected through the Pakka road. and total road length is minimum, and this tree itself is called the minimum spanning tree. Minimum in the sense the minimum weight is there. If you are picking another configuration from this original graph, then the total sum of weights will be more than the weight of this particular tree. So that is not minimum spanning tree, but since the weight of this tree is minimum, so it is called the minimum spanning tree. Spanning means all the vertices of the original graph should be available in this particular tree. So if all vertices are there, then it is called the spanning. If it is satisfying the definition of the tree, then it is called the tree. All vertices are there, then is spanning. If sum of weights is minimum, then it is called minimum spanning tree. So here you can see how many vertices are there. 6 vertices. How many roads? 1, 2, 3, 4, 5. So 6 vertices, 5 roads. All are connected. No loop is there. It means this is a tree. It means this is the minimum spanning tree. So you can say this way we can connect all the villages through Pakka road, and the total road length is minimum. There are popular algorithms also for to find out such minimum spanning tree. One is called the Prim's algorithm. Another one is called the Kruskal's algorithm. Both are very simple algorithms. Okay, where basically all the line features are arranged in ascending and descending order, basically in ascending order, and started connecting those vertices according to the weights, and the definition of the tree should not be violated, and you will get the minimum spanning tree at the end very easily. Okay, now coming to the Chinese postman problem. See, this is the suppose these are the locations. Okay, these are basically network. Let us say post office is at vertex number A. And what is the job of the postman? They want to deliver the letters to individual households. So households may be across the road, somewhere here, not at the vertex. Vertex is basically the junction to connect the roads, but households are across the road. It means they want to go over each and every household. It means, and what is the job? Postman wants to deliver the letters. It means he has to visit each and every road only and only once. If he is traveling roads more than once, it means he is traveling extra and he has to spend more money. So his objective is how to cover all the roads only and only once, and finally coming back to the post office. Starting from post office, going to each and every road, covering all the roads only and only once, and coming back to the post office. So for to explain this situation, I want to show you one network here. If you are able to see this type of the network is very simple, just like a square, and this network is called the Hamiltonian network. Whatever the first square you are able to see, this is called the Hamiltonian network. So what happens, suppose post office is at this corner. So what is the objective of the postman? He can go to this road, delivering all the letters and all in between, and then going to this road, delivering the letters to the individual households, then going to this road, delivering the letters, and then going to this road, delivering the letters, and coming back. So what is happening in this network? He has visited all the roads only and only once, and finally came back to the post office. So this is the Hamiltonian network. It means in Hamiltonian networks, the problem is very simple. Automatically, he's visiting every road only once. But if this type of the network is there, this network is called the Eulerian network. So what happens? Suppose post office is here, or let us say post office is here. Okay, and again the objective is same. You want to visit to each and every road only and only once. Then how he can cover? Suppose he is starting from here, going to this road, then this road, then coming back this road. So this has left. So again he has to go this one. It means he is traveling this road twice. Then covering this road. Then again he has to come back to the post office. It means again he is coming back this. It means he is traveling this road twice and this road twice. he is not able to cover all the roads to visit only and only once, just because of the structure of this network. Whatever the way you identify, you cannot cover all the roads only and only once. It means if network is Euclidean in nature, some roads has to travel twice by the postman. He cannot cover all the roads. He cannot visit all the roads only and only once if Euclidean network is there. So problem arises for the postman if network is Euclidean. In city network, city road network is generally Euclidean in nature. Okay. So point is that the minimum travel distance for the postman is the total length of these roads. Suppose this is 5 kilometer, 5 kilometer, 5 kilometer, 5 kilometer, 20 kilometer, and this is, let us say, 10 kilometers. So total distance he has to travel is 30 kilometers. But because of this nature, he is traveling sometimes, 40 kilometers, because in this base he has traveled this road twice, this road twice, so 5 plus 5, 10 kilometers extra he is traveling. So total travel distance by the postman is 40 kilometers. Though the actual road length, sum of length of the roads is 30 kilometers only. So he is traveling 10 kilometers extra. So now he is searching. Suppose some another type of the network is there. So there may be a situation like he is traveling more than 40 kilometers also sometimes. The minimum cutoff for the road length is 30 kilometers, but sometimes he is traveling 45 kilometers, sometimes 40 kilometers. So now he has to travel some extra length from the required length. So the problem is, whatever the extra length he is traveling, that should be optimized. It should not be very large. Means the extra length whatever he is traveling, that should not be very large. That should be as minimum as possible. So the optimization is over the extra length traveled by the postman. So here you can see this is the Euclidean network. For example, the postman is starting from here. Now again the job is same. He want to cover each and every road only once. But since it is Euclidean network, so he cannot cover all the roads only once. Somewhere he has to move twice. So you can identify the road, any path. Let us say this path. For example, um, this way. Yes. See, when he is visiting, suppose this path, this road, then coming back. This red line is showing basically he is traveling this road twice. So the extra this side means that he is traveling this road twice. So same way it is mentioned. So he is going from here, coming back, then going here, then coming here, then going here, then coming here, going here, then going here, then again coming this way, then going here, coming back here, then going here, then going here, then coming back. So this way he has completed all the roads. But point is, here this road he has traveled twice, this road has traveled twice, this road is traveled twice. So how much extra length he has traveled? 9 kilometer here, 1 kilometer here, 10 kilometer, 3 kilometer here. So total 13 kilometer extra length he has traveled if you are suggesting the path to the postman in this manner. Means you are saying, you please visit this road twice, this road twice, this road twice, and other roads only once. So extra length is 13 kilometer. So now if you are suggesting another, let us say solution, let us say this one, another solution is this one. So what is this? Here the traveling salesman is traveling this road twice, this road twice, and this road twice. So in this case, how much extra length he is traveling? 3 kilometers here, 2 here, 5, 1 here, 6. So only 6 kilometer extra length he is traveling. It means this solution is better than the previous one. In the previous solution, he is traveling 13 kilometer extra. So this route is better than the previous route. So postman wants basically, please suggest a route where the extra length should be as minimum as possible. It should not be, randomly he cannot visit any road twice. If he's randomly visiting, it means that is not the optimization problem. So optimize the network in such a way that the total travel distance, extra distance by the postman should be as minimum as possible. So here you can see, yeah. Okay. So this one 3 kilometer more, and let us say this route is suggested. So this is again extra length, okay? Because 3 and 2 again 2 kilometers extra he has traveled. Suppose now this solution you are recommending him. So how much extra length is there? 2 plus 3 5 plus 1 6 plus 2 8 plus 3 11. 11 kilometer extra he is traveling. Okay. So this 11 is better than 13 kilometers. So you can say this one is the optimum one. So what is the basically how to identify the network is Eulerian or not? So from here, this you can say there is a concept called the degree of the vertices. If the degree of vertices is odd, in odd numbers of vertices, then the network is called the Eulerian. Here degree of vertex means the number of connected lines. Here the connected lines is 1, 2, 3. It means the degree of this vertex is 3. So this is 3. This is also 3. This is also 3, 3, 3, 3. So 2, 2, 4, 6 are having odd degrees. 1, 2, 3, 4, 5, 6. This is having even degree. So if number of vertices with odd degrees are even, then the network is called the Eulerian network. Okay, so the same example here you can see. Here in this vertex is having 2 degree. This is having 3. This is having 2. This is having 3. So the odd degree number of vertices are 2. It means even. So number of vertices with odd degrees are even. The network is called the Eulerian. So instead of suggesting the root first, you can simply check the degree of each vertex. If odd degree vertices are there and number of odd degree vertices even, it means directly you can say this is the Eulerian network and the postman has to travel some extra length, and the optimization can be done over the extra length. Okay. So see, this one is not yeah, optimum one. So this one is okay. Now another problem is called the maximum flow problem. This is useful for the networks, pipeline networks or the water pipeline, gas pipeline. So what it is basically, this is explain the capacity of the each pipeline network. For example, for this particular line feature, the arrow is toward this side. It means the flow of resources is toward this side, and 8 is representing the capacity of the this particular pipe. It means 8 unit of fluid can flow through this particular pipeline. Okay, and similarly, this is the capacity of this line pipeline, and this is the capacity of this one. This is the capacity of this one. So what happens from this particular algorithm or the problem? You can easily identify where we are putting this type of the pipe. If some extra capacity is there, which is useless, or where we are putting some uh, more capacities. Okay, for example, this is the capacity of the pipe, and the so for this particular vertex the incoming capacity is 8 units, and what is the outgoing capacity? This side is 3, this side is also, this side is 9, and this side is 2. Okay, so total capacity is 14 units. So you can say a smaller pipe of 8 unit is connected with this, and total outgoing flow is 14 units. It means the requirement of these 3 pipes cannot be satisfied by this smaller pipe. It means from any of this pipe some extra capacity is useless, means whatever the extra capacity is put it over these 3 lines is useless. So instead of putting larger capacity, you can put some pipeline with the smaller capacity, so that will also be useful. Same way this side, if you see this capacity is 7, and this side how much it is going. So you can say for this vertex incoming is this 2 unit, this is 7 unit. So 9 unit is incoming, and how much is it is going? 6 unit this side, and 5 unit this side. So total 11 unit is outgoing. Means outflow may be 11 unit, but inflow is only 9 units. It means again 2 units extra is there. So the capacity of these pipelines can be decided accordingly. Okay. So in the city network, wherever the pipeline network is there, so the network of the pipeline can be easily identified from source to sink. This is called, let us say, source, and this is called the sink, so that the maximum flow can be possible. Means put the pipeline in such a way that the maximum flow is possible and all the pipelines are utilized properly. No one is vacant, or no one is completely exhausted. Means if it is, suppose this side the capacity is 8 and outgoing the capacity is only 6, for example, then there may be extra load over the outgoing pipeline, so then those pipes may be worst of punctures. Okay, so those kind of the problems may arise. So according to this maximum flow problem, the configuration of the pipelines can be easily identified, so that the maximum flow may be maintained from the source to the sink locations. Okay, so this is applicable over the pipeline network, plus nowadays traffic over road network also it is applicable. Suppose in your city some incoming traffic is there from, let us say, 1 or 2 routes, and then within the city you have to divert the traffic over one road, two road, another road, something like that. So according to the capacity of the each road, you can divert the traffics depending upon the capacity of the incoming roads and the outgoing roads. Okay, so that way it is also useful. So thank you. Actually, this lecture can be explained in a much better way if the things are explained on a board. So at most of the times, if you're not connecting, then you can miss the concept. Because the cursor was not used every time. So if you are missing something, then the flow may be missing. You cannot basically come back to that original concept. Okay, so thank you so much. And now, if you have any questions, we can discuss.
All the participants who have doubt can raise their hand.
Yeah.
Okay, Uzval, why then it Uzval, please ask your question.
Hello, good evening, sir.
Yeah. Good evening.
Hello.
Yes. Yes.
Sir,
Please.
once can you explain how you were calculating the impedances? Like you were saying the numbers from
Yeah,
A to B, B
actually,
to C.
impedance I was explaining the first slide. So somebody was saying so for 52 minutes. Otherwise, I can something I've already explained, like static impedance factors using the travel distance or the travel time. Okay, so distance based calculation is very simple, like the road length. Road length itself is a travel distance, and from the road length you can calculate the impedance. Okay, and if
And
calculating from time, then you have to take the help of the distance equal to speed equal to distance upon time relationship. And for dynamic it is difficult. For that you have to have some devices or the sensors installed on the road, so that we can capture the real time traffic information, and that information can be used to develop some empirical relationship in order to establish the congestion level, so that the congestion level can be directly linked with the impedance factors. So that is called the impedance factor. Yeah, what exactly your question is?
uh, like you have given some numbers right from A, B, I mean A to B, B to C, and
Yes, sir.
you are take some numbers like 5 plus 3 or something like that. I did not
Yes,
understand that part clearly. Once can you again explain that?
that impedance factor.
The addition one. You initially told
Okay,
about the
okay, okay,
slowest
okay.
path problem, right? That addition, how did we optimize for that algorithm you were saying? So,
No, no. This impedance factor is not optimized with the algorithm. This is basically the cost, or you can say the transportation cost, which you have to pay from, let us say, this node to that node, or you can say if you are traveling over this particular road, then how much cost you are paying. So that cost generally we are paying according to the distance. Suppose more distance, more cost. So suppose distance is 5 kilometers, then you can say 5 into per kilometer charges are there. So that per kilometer unit charges you can multiply with this factor. So the total cost you will get. Okay. So more distance, more cost. If you are calculating with respect to time, travel time, it means more travel time, then most travel cost. So according to the time you can assign, suppose you are hiring some vehicle, they are charging 60 rupees per hour, or 200 rupees per hour. So according to the time itself you can calculate the impedance factor.
okay.
Mm.
Okay, sir. Thank you, sir.
Okay. Yeah, any other?
Yes, sir. We have a question from Urbhasha Das.
Okay, what is the question?
Urbhasha, please ask a question.
Yes. Hello, sir. Am I audible?
Yes, yes.
Sir, I have a little doubt on the minimum spinning tree problem. Only the diagram part. Other else I got that. Only the
Okay,
diagram part.
only the diagram part. Okay, I can
Yes.
go back to the, yeah, this one, nah?
Yes, yeah. Only the
uh
minimum tree one.
yeah, minimum spanning tree, I can take help of this network. Let us suppose, what is tree? Tree is a connected graph of n vertices and n minus 1 arcs, all are connected without loop. Suppose this is the network.
Mm.
Okay, so how many vertices? One, two, three. Three
Tree.
vertices and two lines. This is the tree. Okay, if I am suppose connecting another part, let us say this one. So this is still tree. Here you can say four vertices, three arcs. So this is tree. All are connected. No loop is there. Suppose I am connecting from here to here, this one, then this is not tree, because now you are getting the loop. Okay, so this is the definition of the tree. Sorry, control. So this is the definition of tree, means n vertices, n minus 1 arcs, without loop, all are connected. Okay, so that is the definition of tree. But suppose one network is given, so in that network some number of vertices are there. It means number of vertices are fixed in that network. So now if you are creating a tree which consists of all the vertices of this given network, for example, in this network, 6 vertices are there, and if you are creating a tree which is also having all those vertices, let us say 6 vertices, then this network or this tree is called the spanning tree. Okay, so then the next term is called the minimum spanning tree. Means if from this particular graph I can draw many spanning trees, I can draw like this also. Means from here to here, here to
Mm.
here, here to here, here to here, here to here. This may be a spanning tree because all the vertices are there. You just concentrate on the cursor on. Are you able to see my screen? No?
Yes, sir. Yes, sir.
Yes. Suppose I am drawing one another spanning tree. Let us say from here 1 to 2, 2 to 3, 3 to 5, 5 to 4, 4 to 6. So all vertices are covered, and
Yeah.
definition of tree is also mentioned. So that is also another spanning tree. Okay.
Mm.
I can draw another one. Let us say 1 to 3, 3 to 4, 4 to 5, 5 to 6, and 3 to 2. That is another spanning tree. But if I'm calculating the weight of all those trees, for example, in this tree, the total weight is 16 plus 11, 27 plus 5, 32 plus 6, 38 plus 18, 56. Means the weight of this spanning tree is 56. The same way, I can calculate the weight of other spanning trees which I have extracted from this given graph. Okay, so the sum of weight for those spanning trees may be different, maybe sometimes more than 56 or less than 56. Okay, so suppose the weight of one spanning tree, let us say 1 to 2 19, 2 to 3 23, so this is 42, and then 3 to 5 14 ho gaya. So 41 plus 42 plus 14, uh, 56, 56 plus 5, 61, 61 plus 6, 67. Means the weight of this tree, this spanning tree from 1 to 2, 2 to 3, 3 to 5, 5 to 4, 4 to 6, the weight is 67. If I'm taking another spanning tree, let us say 1 to 3, 21, to 3 to 2, 23, so 44, plus 3 to 5, 44 plus 14, 56, 56, then 3 to, let us say 4, 11, 67, 60, then 4 to 6, 67 plus 6, 73. Means the weight of this spanning tree is 73. It means if you are extracting the spanning trees from this given graph, the sum of weights of those spanning trees are different. And from this graph, n number of spanning trees I can extract. Then I will calculate the weight of all the trees, and I'm interested in a tree which is having the minimum weight among all possible spanning trees. So this is the spanning tree which is having minimum weights. So point is, if this particular network is having n number of possible spanning trees, then question is how to extract the minimum spanning tree from this given graph directly. Means without writing so many spanning trees from this network, how we can extract directly the minimum spanning tree from this particular network. So for that, the algorithms are required. So I mentioned the Prim's algorithm and the Kruskal's algorithms, which can be used to extract the minimum spanning tree from a given graph directly without without extracting so many spanning trees and then identifying the minimum spanning tree. Okay,
Okay,
so
sir.
those algorithms can be used to extract this type of the minimum spanning tree.
Okay, sir. Thank you.
Okay. And in this way, see, from this given graph or given network, so many trees we are able to extract. So sometimes this graph is also called the forest, because from forest so many trees you can extract, and the same behavior this graph is doing. Okay, so from this given graph so many trees we are able to extract, it means this is a forest. So the graph sometimes called the forest also. Yeah, any other question?
Yes, so we have a question from Shantanu.
Yeah, what is the question?
Sir, hello, sir, am I
Yeah.
audible?
Yes.
Sir, my first question is, sir, what is the difference between a direct and indirect network apart from the direction parameter? मतलब डायरेक्शन पैरामीटर को छोड़ के हम और क्या पैरामीटर कंसिडर कर सकते हैं कि हम एक डायरेक्ट और इनडायरेक्ट नेटवर्क को डिफर कर सकें?
Yeah, see, differ means, for example, in this minimum spanning tree solution, that network is undirected. Okay, where see the regular flow of resources is there, so there we have to mention the direction. So those network are the directed network, whether the canal networks or the river network, transmission line network, all are directed networks where the flow of resources is fixed. If it is only one, then unidirectional. If it is in both the way, like road network may be unidirectional or the bidirectional also. But whatever I have shown here in case of minimum spanning tree, direction is not mentioned. So what is happening here actually? Here the objective is to connect, let us say, village 1 and 4, and this cost you have to expand. Okay, it means the construction cost for this particular road is 16 units, 16 lakhs or crore, something like that. So doesn't matter you are constructing this road from this side to this side or this side to this side, means the direction of construction is not important in this case. So from either direction, if you are constructing, the total construction cost will be same. So, and later on the movement will be there. So that is another problem, that may be shortest path problem, closest facility problem, or vehicle route problem, that comes later. So point is, if what is your objective? If objective is something which is not somehow related with the flow of resources, direction of flow of resources, those networks we are generally considering as a undirected network. Okay, so see, because this is the policy, means the policy decisions, means which road we have to pick for the construction of the minimum spanning tree. Then it may be cost like, suppose here it is 16 units cost, but sometimes this cost may increase. For example, this side some elevation is very low, some river is passing, then you have to construct some bridges, etc, etc. Then the cost will increase abruptly. Okay, so in that case, the cost of bridge you have to include, and then you have to decide the impedance factor for this particular line. So it may go up to, let us say, 24 units or something like that. So point is, if flow of resources is not that much important, so in those cases we are considering as a, undirected network. If flow of resources is important to consider, then those examples we are considering as a directed network.
Okay. Sir, I am having a second question.
Yeah.
Sir, what is a static impedance factor, sir, and how to determine that? What are the parameters involved in that?
Have you attended the first slide?
Yes,
I
sir, but
spoken
little
there
bit I
40
couldn't
minutes.
understood.
See, static means fixed, correct? Fixed means if you are calculating the impedance factor, which is almost fixed, not varying with the time. So that is called the static. Suppose you are calculating the impedance factor from the distance. So distance is fixed between the 2 points. Distance is not going to change. It means if you are calculating the impedance factor from the travel distance, distance is fixed between the points, it means that is called the static impedance factor. Okay, and if you are calculating the time, but time, if time is changing with respect to the day or the time of the day, then it is called the dynamic. Otherwise means if you are calculating time by some another means, let us say the speed equal to distance upon time. So distance is fixed, you want to calculate time, and you are using some speed, and we have taken the example of the speed limit. So speed limit is also fixed. Speed limit is fixed, distance is fixed. It means whatever the time you are calculating, that is fixed. If that time is fixed, that is called the static impedance factor. If this time you are calculating from the actual traffic conditions on the road, then this time may fluctuate, according to the time of the day. So that is called the dynamic impedance factors. So dynamic means it is fluctuating with respect to time. If it is fluctuating, then dynamic. Not fluctuating, it means it is constant, then it is static impedance factor.
Sir, I have last question. That's
Mhm.
my third question.
Mhm.
Sir, are the spatial data used for the construction of bridges and roads?
Which data?
Spatial data, sir. Spatial data. That remote sensing data are used for construction of bridges or roads.
See, that is not related to this lecture, but yes, every time we are using the satellite data sets for the construction of building. Nowadays, people for the construction of highways also, people are using the satellite data because they want to check the stability of the highways. Means stability of the land where they can construct the highways. It means that stability can be checked with the help of the satellite data. So satellite data is useful everywhere. So see, whatever I have explained, the point and line features in case of this graph theory or the network, these lines or the points are coming from where? Using the satellite data.
Satellite.
Yes. So in the background, we are using the satellite data, and over that we are digitizing this vector data, and later on we are performing the analysis. Okay.
Sir, can we determine the this means the problems like, sir, somewhere the highways gets cracked or somewhere the bridges gets collapsed? I'm taking an example of the Bihar, sir, where 5 bridges have
Yeah,
consecutively
collapse
collapsed
means some
few
damage,
months before.
some damage is there. Yes, for that some specialized techniques of the remote sensing needs to be applied. For example, the microwave remote sensing data sets, that is called radar data set, where the spatial concept is there called the interferometry, SAR interferometry. So SAR interferometry, some advanced techniques can enable you to find out any kind of the damage or deformation in the structures, whether it is road or the bridges or the dams or even the land subsidence or the volcanic eruption, earthquake, or even the cracks in your building. So that is very what I'm telling. Basically, crack is there. It means that is very small thing, and that small thing can be monitored from the advanced techniques and specialized radar data sets. Microwave data sets are the radar data sets in this particular case. Okay. So what we are doing there, we are calculating the phase difference of the two signals. So that phase difference is calculated. So phase difference is equal to 2 pi upon lambda into path difference. Path difference is nothing but the movement of target from its original position to the new position. So suppose some damage is there or some tilting is there in the bridges or some shifting, small scale shifting, even the millimeter scale shifting is there. So shifting is from this location to this location. Let us say 1 millimeter shifting is there, or 2 millimeter shifting is there, or 10 millimeter shifting is there over 1 year of time. So this shifting is basically the path difference, and path difference can be calculated from the phase difference. Phase difference is coming from the two signals of the radar data set. So this path difference can be calculated. It means you can identify how much shift or tilt is there in the bridges with respect to the previous date, and if this shift is continue for longer period of time. So the means time series behavior you can analyze from number of satellite images. Then you can have idea, okay, this bridge is continuously moving in this particular direction or not. If it is continuously moving, you can predict also what is the life of the bridges, or after this time what can happen, or whether the bridge is going to collapse, or is any other type of the damage may happen. So such kind of the analysis can be done. Okay, so tomorrow I will explain something about this, when I will explain about
Thank you,
the.
sir. Thank you very much. Thank you, sir.
Okay. Yeah, any other question?
Is there any other participant who has any question? Dr. Arundhati, please ask a question.
Sir, which sensors are used in order to know the shortest distance?
Yeah, not able to hear you.
Sensors you're saying.
Dr. Arundhati, you are not audible.
Sensors. Which sensors are used, sir?
Dr. Arundhati, you are still not audible properly.
Sensors. Which sensors are used in knowing the shortest distance, sir?
Yeah, not able to get your point.
Which sensors is used, sir?
Uh,
Sensors.
So I guess there is some problem in the mic. If you want, you can write the question in chat and I'll read it out for you.
yeah, one question is there. How very interesting question. How does Google find out whether there is a traffic jam or not? Yeah, very interesting question. Actually, everybody is using the Google Map, and whenever we are moving in a high tech city, so that time on Google Map we are able to see, some color codings, somewhere red, somewhere orange, somewhere green, something like that. So this is somehow related with the traffic situation on the road in real time manner. Not exactly real time. It is a combination of the real plus historical data sets over that particular road. So how they are using, basically collecting the data set from the smartphones. You have the smartphone, you have the internet connectivity in your mobile, plus you have the GPS connectivity. Wherever you are moving, it means you are using the GPS locations also. Okay, and these two informations are captured by the Google. So suppose you are moving with your smartphone, your GPS is on, internet is on, and you are also basically exploring the Google map, so your data is going there. And now they are capturing, okay, how many smartphones are there on this section of the road, and location is there on the road, data is there, location is also there. Okay, and not only location, why which speed you are moving, that speed is also with them. So from your data set they can have idea. Suppose 100 mobiles are there in a particular section of the road, it means they can have idea, okay, how much traffic is there. More number of mobiles means more number of traffic, or traffic density is high. And what is the speed of this each mobile is with you and you is with the traffic. It means if speed traffic speed is less, his mobile speed is less. It means they have idea, okay, speed is very slow. So they are developing empirical models. Let us say more speed, no congestion; less speed, more congestion. Inverse relationship is there. Speed is high, low congestion; speed is low, high congestion. Correct. Another one, the number of traffic or number of vehicles, more traffic, more jam; less traffic, less jam. Okay, it means direct relationship is there. So from these traffic parameters they are collecting this data smartly and putting in the color coding over the roads. Okay, over this road at this time this much traffic is there, and if speed is less, then they are highlighting by red color. If more traffic is there but the speed is very fast, then they are putting, orange color, or less density is there or moderate speed is there, then they are accordingly, basically they are deciding the color codes. Okay, if speed is fast, number of traffic is also less, then they are putting green. So so in nutshell you can say, I would say, Google is collecting your data from your smartphone to their server, and they are assigning the colors to the each and every road. So real time data they are collecting, plus the historical data is also there. Means every time, every day, what is the situation over this particular road at 12 o'clock or 3 o'clock or 4 o'clock. So yesterday 4 o'clock data is also coming today at 4 o'clock. So some component of weightage is there from yesterday or day after, day before yesterday. So the historical data plus real time data both are clubbed together, and finally the decision is being taken. Okay, but keep in mind this decision can be altered. For example, suppose you are sitting in your small van, and in that van you are putting 100 or 200 mobile phones. Internet is on in all 200 mobile phones. GPS is on in all 200 mobile phones, and you are moving on a particular road. So the data is going from all the 200 mobile phones. Google will show that section as red because density of the mobile phone is very high. In reality, suppose traffic is not there, but in your device, in your vehicle, 200 mobile phones are there, and because of these 200 mobile phones it will show the red color. Okay, so those can be altered, but generally in practical life such situations are not there. These are very typical situations where unknowingly you are putting 200 mobile phones but nobody is having. Okay, so that way it is captured. Google is capturing this real-time information and uh, putting for the public. Okay, I think now it is fine. Yeah?
So, shall I end the session now?
Yes, please.
Thank you, sir, for such an insightful session. Thank you, all the participants. Now you all can leave the meeting.
Okay, thank you.